Hi, everyone, and welcome back to Clean Tech Deep Dive.
Great to be back.
In our last exploration, we looked at the big picture, how the world is moving towards renewable energy
A
sources.
huge shift, definitely.
But to really make that renewable future work, there are two crucial pieces we absolutely have to talk about: smart grids and energy storage systems, ESS.
Yeah, they're completely essential. You can't really have one without the other, not effectively anyway.
Exactly. So, in this deep dive, we're going to unpack how these two work together to build a cleaner and, maybe just as importantly, a more reliable energy system for all of us.
hmm
We've gathered insights from, well, all over government research, labs, market reports, looking at what's happening globally, too.
Yeah, lots to cover.
Our goal is simple, really: give you the core understanding of smart grids and ESS. Without getting totally bogged down in the super technical stuff, hopefully you'll have a few aha moments.
Sounds good. And, shifting to a grid powered mainly by sun and wind,
Mhm.
it really does throw up some fundamental challenges.
How so? What's the main issue with the old way?
Well, the way our traditional electricity system was designed, these big power plants had to constantly adjust their output, like second by second, to match exactly what everyone was using.
Right, a constant balancing act.
A balancing act on a massive scale, yeah.
Yeah.
Electricity is this funny thing. You pretty much have to use it the moment it's generated.
Or it's just wasted, gone.
Exactly.
Yeah.
And that led to some pretty, let's say, inefficient workarounds, like
Yeah.
building the grid to handle those rare, super high peaks in demand.
I read a great analogy for that somewhere. Like building a 30-lane highway just in case everyone decides to drive at the exact same time.
That's a perfect way to put it. It gets the job done most of the time, but it feels like there has to be a smarter way, right?
Absolutely. And that, I assume, is where smart grids come in.
Precisely. The official line is something like an upgraded grid using cutting-edge technologies, equipment, and controls that communicate and work together.
Yeah.
But the core idea is making our electricity system more resilient, more efficient, and much more responsive to what we actually need.
Okay, let's unpack this smart idea then. It sounds like more than just laying new tables. What makes it fundamentally different?
Oh, definitely more than cables. The goals are pretty broad.
Hmm.
We're talking fewer power outages, less disruption from storms.
Faster restoration when things do go wrong.
Exactly, getting the lights back on faster. And also giving you, the consumer, more insight and maybe even control over your energy use, your bills.
And for the utilities, what's in it for them?
For them, it's things like better security against cyber or physical attacks,
Mm.
being able to reduce those really expensive peak demand loads,
Which saves money.
big time. Plus, much easier integration of all that renewable energy coming online and ultimately lower operating costs. It's really about making the whole system more, well, intelligent.
So it seems like a win-win. A smarter grid benefits pretty much everyone. But what are the actual technologies making this happen? I hear terms like advanced power electronics, intelligent communication. What does that mean in practice?
Those are definitely key pieces. There's a lot of investment going into these next-gen technologies.
Yeah.
A really critical area is grid-scale energy storage, which we'll dive into more deeply in a bit.
Okay.
But beyond storage, we're also talking specific R&D for smart grids themselves. Things like solid-state transformers, which are way more efficient than the old ones.
Mm-hmm.
Adaptive networks that can automatically reroute power if there's a fault, almost like the internet does. Then you've got the sophisticated communication systems,
Mm-hmm.
the grid's nervous system, really in powerful data analytics to make sense of it all and make better operational decisions.
And I saw some research breaking it down into three key areas: transmission, the big power lines; distribution, the local neighborhood lines; and then end use, which includes things like rooftop solar, right?
Yeah.
DERs.
That's a really helpful framework
Mm-hmm.
because a smart grid is all about increasing both visibility, basically, knowing what's happening on the grid in real time.
Seeing everything clearly.
Yeah, and control, the ability to actively manage that flow of electricity. It's like upgrading from an old paper map to a live interactive ways for the entire power system.
Okay, so there's better visibility and control. What does that actually let you do? What are some real-world functions of a smart grid?
Well, researchers highlight several key things, like the grid being able to self-optimize, meaning it can automatically adjust itself based on conditions to run more efficiently. Think of it like a smart thermostat, but for the entire power grid.
Wow.
It also allows for more targeted reliability, so maybe critical places like hospitals get higher levels of backup. Greater efficiency just through automating grid operations from end to end.
Less manual switching and stuff?
Exactly. And crucially, especially for renewables, it allows for much better optimization of clean resources, making it easier to integrate solar and wind smoothly.
That makes a lot of sense. So it's not just one single thing, it's this whole ecosystem of improvements working together. I also saw mentions of like demand management and those smart digital meters everyone's getting.
Yeah, those are important parts too. Demand management lets utilities, say, encourage people to use less energy during peak times, maybe through pricing signals, or even automatically make tiny adjustments, like briefly dimming lights in big buildings to avoid firing up an expensive power plant.
And the smart meters.
Those advanced meters provide that constant stream of data on energy use. It helps both you and the utility make smarter decisions. Other pieces include things like local power hubs, online tools to track your energy, automating the local distribution network to quickly isolate problems.
Like if a tree falls on a line.
Right. Fix it faster, impact fewer people. Then there's managing electric vehicle charging so it doesn't overload the system, and smoothly integrating all those distributed renewables, like your neighbor's solar panels.
Oh.
And underpinning all of this, you need a really robust communication and IT network. It's the backbone that lets all these smart components actually talk to each other.
Right, which brings up a big question. With all these different devices and systems from different companies, how do you make sure they can all, understand each other? Seems like it could be chaos otherwise.
That's a huge challenge, and that's where interoperability comes in. It's absolutely critical.
Interoperability, making things work together.
Exactly. It's the ability of all these different devices and systems, meters, inverters, utility control systems, you name it, to communicate and function together seamlessly. Think of it like ensuring all the different apps on your phone can actually share data and work together smoothly.
Okay. Are there standards for this?
Yes, thankfully. Things like the IE 2030 standard are really important guides. They focus specifically on integrating the energy technology side with the information and communication technology side.
So everyone speaks the same digital language, more or less.
That's the goal. And it has to work at the big system level, like utilities exchanging data, and right down to the device level, so your smart thermostat can actually respond to a signal from the grid operator. It covers the power, the communication, the IT, everything.
It sounds like a massive undertaking just to get the standards right. I know some of the big national labs are heavily involved in testing all this stuff too.
They absolutely are. Places like NREL, the National Renewable Energy Lab, have been instrumental. They help develop these crucial standards like IE 2030 and 1547 for interconnection.
And they test things?
Extensively. Their facilities let them push the limits, see how much renewable energy we can really integrate, test advanced distribution systems like microgrids, figure out the best ways to control storage and other resources, and they develop the actual test procedures to certify that equipment meets the standards.
I think I read about a specific technology they developed, Grid Agent, something about two-way communication.
Yeah, Grid Agent is a good example. It's essentially a platform designed to manage and coordinate all those distributed energy resources, DERs, based on what they can do and what the grid needs at that moment.
Very cool.
And they also test other hardware, like advanced switches for microgrids or combined heat and power systems that use smart inverters to interact better with the grid.
And there are real-world examples popping up now, right? Like that microgrid project in Portland using smart inverters and storage.
Exactly. Seeing these projects actually being built helps connect the dots.
Yeah.
These localized microgrids, often with their own generation and storage, can really boost resilience, especially during outages.
And if you zoom into a smart home within this system, you see how it all fits together.
Right. You've got maybe solar panels feeding energy back, your EV charging smartly, appliances responding to price signals, systems measuring your usage,
Yeah.
all potentially visible through online portals for both you and the utility.
It's this really intricate web, isn't it? Communication and control from the big energy markets right down to the toaster, potentially.
Well, maybe not the toaster yet, but yeah, the level of coordination is increasing dramatically.
Okay, let's zoom out again. We've talked a lot about the U.S. context. Is this smart grid stuff happening elsewhere? What's the global picture look like?
Oh, absolutely. It's a global trend driven by the same needs for resilience and renewable integration. Asia, in particular, is seeing massive investment.
Like where?
Well, China has a huge national grid modernization plan running right now, focused heavily on integrating renewables, demand response, making the grid more flexible.
And Japan. They always seem to head on efficiency and disaster resilience.
They are.
Yeah.
Japan's a leader, holds a big chunk of the Asia-Pacific smart grid market, and they're investing heavily in storage, too. South Korea is also pushing hard, especially in cities, for better energy management and grid reliability, plus lots of R&D.
What about India? I heard about a really ambitious plan there.
Yeah, India is interesting. They're expanding hydro-based storage, including huge pumped hydro projects, and they have this One Sun, One World, One Grid initiative aiming to connect grids across Asia and even Africa. A truly massive vision.
Wow.
You see similar trends elsewhere. Vietnam is looking to export renewable power, which needs grid upgrades and storage. Singapore is diversifying imports, including renewables, and involved in that huge Australia-Asia Powerlink project.
Which involves long-distance transmission and storage, right?
Exactly. Laos is leveraging its hydropower, becoming like the battery of Southeast Asia. Even the Philippines are rolling out pilot projects to improve access and stability.
So it's clear smarter grids are a global necessity for this energy transition. Okay, let's switch gears now to the other crucial piece you mentioned, energy storage systems,
Oh.
ESS. You called them a holy grail earlier. Why is that?
Well, it really comes back to that fundamental issue with renewables like solar and wind. They're variable, intermittent.
They generate power when nature decides, not necessarily when we need it most.
Precisely. So grid-scale energy storage lets us capture that clean electricity when it's plentiful sunny day, windy night, and save it for later. Decouple generation from consumption, essentially.
Hold on to the electricity for a bit.
Exactly. As one article put it, just hold on to it and use it later. This drastically reduces that need for constant real-time balancing. It means we might not have to overbuild the grid quite so much for those peaks.
And it opens up other possibilities too, right? Like local backup power.
For sure. More resilience, maybe more decentralized grids where communities have more control. It's a game changer.
And we've seen this absolutely massive boom in storage recently, particularly lithium-ion batteries. A gargantuan surge, I think, was the phrase.
That's no exaggeration. Just look at the U.S. numbers.
Yep.
Between 2021 and 2024, battery storage on the grid increased fivefold.
Wow.
In 2024 alone, 12.3 gigawatts were added. And projections show we might nearly double that this year.
That's incredible growth.
And here's a milestone. Total installed battery storage capacity has now actually surpassed pumped hydro storage capacity. We're over 26 gigawatts of batteries now. That's huge.
So what's driving this explosion? It feels like a perfect storm of factors.
It really is several things hitting at once. First, and maybe biggest, is the dramatic drop in lithium-ion battery prices, coupled with improvements in how much energy they can hold their energy density.
How much have prices dropped?
We're talking maybe $3,000 for kilowatt hour back in 2008, down to, well, maybe $150 to $200 per kilowatt hour for a fully installed system today. Just incredible cost reduction.
And why did that happen?
A big part of it is the massive scale up in manufacturing, driven by, laptops, phones, and especially electric vehicles.
The EV effect.
Exactly. As one expert said, it's all one big pipeline. Innovations and cost reductions for EV batteries directly benefit grid batteries.
And China's role in manufacturing.
Huge. They now produce something like 80% of the world's lithium-ion batteries, and that scale has driven global prices way down.
Okay, so cheaper, better batteries. What else?
Well, the sheer growth of wind and solar creates the demand. Batteries are the perfect partner to smooth out their variability. Think about this. In 2024, solar projects paired with storage made up 84% of all new power capacity added in the U.S.
84%. That's stunning.
It really shows how intertwined they've become. Plus, grid batteries have an advantage. They don't need to be super small or lightweight like in a car.
Right, they can be bigger, maybe use slightly cheaper chemistries.
Potentially, yes.
Yeah.
And there's also the possibility of using second life EV batteries for grid storage once they're no longer ideal for driving. Extends their useful life.
Smart. And policy must play a role too.
Definitely. You've got 11 states now with specific targets for utilities to procure energy storage. That creates a guaranteed market, drives investment, encourages new businesses. It all adds up.
So ESS is like the peanut butter to renewable energies chocolate, making it work reliably.
Yeah, that's a good way to put it.
But beyond just firming up renewables, what else do these storage systems do for the grid and for us?
Oh, they do a lot. They're critical for overall grid stability, reliability, resilience. They can provide backup power during outages, keep essential services running during extreme weather.
So resilience is key.
Huge. And they can also help defer or avoid expensive upgrades to transmission and distribution lines. Instead of building bigger lines just for peak demand, you can use storage to inject power locally when needed.
Like a flexible reserve, deployable anywhere.
Exactly.
Yeah.
It acts like a shock absorber for the grid in many ways.
And I know they provide a whole list of what are called grid services. Can you unpack that a bit?
Sure. Grid services are basically all the background jobs needed to keep the electricity system running smoothly.
Mm.
ESS is really good at many of these.
Like what?
Things like frequency regulation, keeping the grid's electrical heartbeat steady at 60 hertz or 50 hertz elsewhere. Peak shaving, knocking down those expensive demand spikes. Demand response, providing power when the grid operator signals a need. Voltage support, providing reserves like backup power, ready to go instantly. Energy arbitrage, buying low, selling high. Black start capability, helping restart the grid after a total collapse.
That sounds incredibly important.
It is. Also firming renewable capacity, making wind and solar seem more like traditional power plants, controlling power oscillations, shifting energy supply over time. It's a long list.
And these services have different durations, right? Short-term versus long-term?
Yeah, you can roughly group them. Some services are very fast, sub-second or minute responses. Others are medium-term, maybe providing power for an hour or a few hours. And then there's long duration, providing power for, say, 10 hours or more.
Okay, so ESS is like a Swiss Army knife for the grid.
Yeah.
Now, lithium-ion is dominant now, but you mentioned other technologies earlier. What else is out there?
Right, lithium-ion gets the headlines, but there's a whole portfolio of other storage techs being developed and deployed, each with different strengths.
That's right.
You've got flow batteries, redox flow batteries, which store energy in liquid electrolytes in tanks. They look promising for longer durations. Supercapacitors store energy electrostatically. Superfast charge and discharge, great for power quality. Flywheels use a spinning rotor kinetic energy, also faster response, good for frequency regulation.
What about hydrogen? Hear a lot about that.
Hydrogen's a big one, especially for long duration. You make it using electricity, often through electrolysis, store it, then convert it back to power using fuel cells or turbines. Challenges remain, like efficient storage and making sure it's green hydrogen made with renewables.
All right.
Then there's superconducting magnetic energy storage, SMES, very efficient, but currently expensive and niche. Thermal energy storage, storing heat or cold, used in things like concentrated solar power plants with molten salt. And we can't forget pumped hydro, still the biggest source of storage capacity globally, basically pumping water uphill.
So it's definitely not a one-size-fits-all solution. The best tech depends on the job. And I've also heard about hybrid energy storage systems, HESS, combining techs.
Exactly. HES is about leveraging the complementary strengths. Maybe pair batteries, good for energy capacity, with supercapacitors, good for high power boosts.
Get the best of both worlds.
Sort of, yeah. By combining them smartly with sophisticated controls, you can optimize for specific tasks like grid stability or smoothing renewable output more effectively or cost efficiently than with just one technology. We're seeing real-world HESS deployments now.
Now, that longer duration storage you mentioned, LDES,
Yeah.
that seems absolutely vital if we want a grid running mostly on renewables, right? To get through cloudy or calm spells lasting days.
Absolutely critical. LDES, typically defined as 10-plus hours of storage, is essential for resilience and for bridging those longer gaps in renewable generation.
And what technologies look most promising there?
Hydrogen is definitely a major contender. Gravity-based systems are also getting attention, basically using electricity to lift heavy weights and then lowering them to generate power.
Like a modern version of pump hydro, but with weights?
Kinda, yeah. There are some interesting projects like the big green hydrogen storage hub planned in Utah or gravity storage tests in the UK. Still early days for some of these at large scale, lots of technical hurdles.
Any other approaches to LDES?
Well, another way is aggregating lots of smaller distributed batteries. Think thousands of home batteries, like Tesla Powerwalls or Sun systems, coordinated together. Programs like Green Mountain Powers are showing this can effectively provide long-duration grid services, too.
Fascinating. But managing all this, renewables, different types of storage, all connected through power electronics instead of old spinning generators. How does the grid stay stable? Doesn't it lose inertia?
That is a huge concern. You're spot on. Traditional power plants with big rotating generators inherently provide inertia, which acts like a shock absorber against frequency changes.
Keeps things steady.
Exactly. As you replace those with solar, wind, and batteries connected via inverters, power electronic converters, the grid's natural inertia drops. This makes it more vulnerable to sudden frequency dips or spikes if there's an imbalance.
So what's the solution?
Two key things. First, developing grid-forming capabilities for those inverters. This means programming them to actively help stabilize the grid frequency and voltage, behaving more like traditional generators.
Making the inverters smarter.
Much smarter, yeah. And second, using energy storage itself to provide grid stability services. ESS can inject or absorb power incredibly quickly to counteract disturbances, providing virtual inertia and fast frequency response.
So storage isn't just storing energy, it's actively stabilizing the system too.
It has to, increasingly. It's a dual role.
Okay, this is complex stuff. How do we even test all these different storage technologies and their grid services reliably before deploying them widely? Seems tricky.
It is a major challenge. You can do computer simulations, of course, great for planning, but they often miss real-world complexities and fast dynamics.
Right.
Lab testing is better, you have controlled conditions, but you don't get the feedback from a real dynamic grid.
So what bridges the gap?
A technique called power hardware in the loop, or VHIL, is becoming really important. You connect the actual hardware, the battery, the inverter, to a powerful, real-time computer simulation of the grid.
So you get real hardware interacting with a simulated grid.
Exactly. It offers a good balance of realism and flexibility. Lets you test dynamic responses like frequency support or inertia provision under all sorts of simulated grid events. Several big labs in Europe and the US have major viable facilities now.
Like NREL and Sandia here.
Yeah, NRL's Ares platform and Sandia's storage and power electronics programs are heavily involved in this kind of validation, testing everything from performance to safety under realistic conditions. And then, of course, there's field testing on the actual grid. Highest realism, but expensive, less flexible, and potentially disruptive.
Makes sense. One last area, sustainability and safety. As we deploy potentially millions of batteries, what are the long-term considerations?
Very important points. On sustainability, the big push is towards a circular economy for batteries. That means designing for reuse, repurposing, and ultimately recycling.
Like Second Life EV batteries we mentioned.
Exactly. And developing efficient, cost-effective recycling processes, especially for lithium-ion, is crucial. We have good systems for lead-acid batteries, but lithium-ion is more complex due to different chemistries. Concepts like a digital battery passport could help track materials through their life cycle.
And safety. We hear about battery fires sometimes.
Safety is absolutely paramount. Lithium-ion batteries do carry a risk of thermal runaways under certain fault conditions or damage. There have been incidents.
Yeah.
So there's a huge amount of work going into safety at every level, improving battery materials, designing safer cells, implementing sophisticated monitoring and management systems within the battery packs, and developing fire suppression, specifically for battery installations. Rigorous safety testing and standards, like UL standards in the US or IEC internationally, are critical for ensuring safe deployment.
Okay. So wrapping this all up, it really feels like smart grids and energy storage systems aren't just helpful additions. They're completely fundamental to making this clean energy transition actually work.
They are absolutely intertwined and essential. You need the smart grid for the communication, control, and optimization, and you need the energy storage for the flexibility and reliability, especially with high levels of renewables.
They work together to tackle those core challenges of variability and grid management, making the whole system more adaptable, more dependable, and ultimately cleaner.
Precisely. It's about creating an energy system that's fit for the 21st century, one that can handle the dynamic nature of renewables and deliver reliable power when and where we need it.
And it's engineers who are making it possible for us to use energy more efficiently, more intelligently, and more reliably.
A lot of innovation happening for sure.
Thanks for joining us today, and until next time, stay curious and stay energized.